Hello and welcome back, everyone. I'm Lee Arkanal from Cyborg Security, and thank you for joining me for another Threat Hunt Deep Dive video. Today we'll be looking at User Account Control, or UAC, bypass through Registry Key Modification. We'll also demonstrate what this looks like from the adversary perspective, as well as learn how to detect it on our network using a SIM. In case you missed our previous episodes, you can find them all on Cyborg Security's YouTube channel. Alright, let's get started. Before we demonstrate a UAC bypass, we need some background information first. For starters, why is this relevant? Why should the cybersecurity community be concerned with this type of attack? What is the auto-elevate property, and how can I find which executables have this property set? We're going to explore some of the tools we use to investigate, and we're going to cover some best practices we can implement to mitigate these attacks. Finally, we will demonstrate 2 UAC bypasses and use Splunk to detect both. So why is this relevant? An easy answer is that multiple families of malware have been discovered to contain this technique within their code. Most notably is the recent attacks on companies with DarkSide ransomware. At some point during infection, DarkSide exploits a Windows native dynamic link library, or DLL, to gain privileged access. As always, I will share the links in the description below. So I know I've been throwing around the term UAC a lot so far, and have failed to mention what it is and what it looks like. So here it is. If you work in an organization that requires changes to be made by an administrator, you may have come across this pop-up in your day-to-day work, preventing you from making the changes that you wanted, whether it be installing a new executable or changing your desktop to the classic hang in there cat. Windows introduced the user account control when Windows Vista and Windows Server 2008 was developed. The goal is to prevent common users from modifying the Windows box and stray from its current setup, which most likely has had some hardening done to it. In essence, the goal is to maintain the security posture of the Windows box as it is. Here's a quick list of some of the Windows native executables that can be exploited by modifying certain registry keys. This is not an exhaustive list by any means, but these executables have been proven vulnerable in laboratory environments. Today in our demonstration, I will be using the executables SDCLT and WSReset to open a command prompt with administrative privileges. SDCLT allows users of Windows 7 and above to perform backups and restore operations, while WSReset is a tool that is used to troubleshoot the Windows Store without changing any account settings. Now that we've covered what UAC is, let me shine some light on the registry and what it does. Instead of reinventing the wheel, I will read straight from the Microsoft documentation. The registry is a system-defined database in which applications and system components store and retrieve configuration data. Basically, the registry key holds certain values that provide instructions for the executables. If these values are changed, the executable can behave in a way which was not originally intended, which we will prove in the lab today. Here we have the registry key related to Excel. One value that sticks out is the path, which coincides where we can find the executable on my box. Now that we know that registry key modifications can change the way an executable acts, can it change other things? In an anomalous example, I created the 2 registry keys listed below to force my Windows apps to open up default in dark mode. I know it's a simple before and after shot, and you may be asking me, I can do that through settings, what does this prove? Well, if you're going to conduct this own experiment on your own machine, do me a favor. Go into the registry, see what values exist, and then once you change it to dark mode, let me know what values changed. Have values changed? Have they been added? Has anything been removed? And if you feel like it, leave your results in the comments. I know it was a simple change, but by creating registry keys, we were able to change the way that Microsoft Windows apps looked by default. Once we get to the demonstration, I will show you how, by modifying an existing registry key related to WSReset, we can gain admin privileges to command prompt. Also, we'll be creating a new registry key related to SDCLT to gain admin privileges to command prompt. Both of these executables are found on Windows boxes by default. While we know that the technique relies on modifying or creating registry keys, the bigger question is, how do we know which registry keys to modify or create? Using a tool from Windows sysinternals called Procmon, we could look at the behind the scenes of the executables that we're targeting. Also, another tool that we can use to find the auto-elevate property that I mentioned earlier is SigCheck. SigCheck is a command line utility that shows file version number, timestamp information, and digital signature details and can be found in the Windows sysinternal suite. By running the listed command against sdclt.exe, we get the output on the right. Looking at the very bottom in the highlighted section, we can see that the auto-elevate property is listed to true. What does auto-elevate mean? Well, if an application has auto-elevate property set to true, it means that it is a trusted binary signed with a Microsoft certificate and located in a trusted directory. Also, if the application is trusted, then in some circumstances, the user account control prompt will not engage. Process Monitor, or procmon, is another tool found in the Windows sysinternal suite. What it does is monitor operations conducted by executables and outputs their values. When we run this against sdclt.exe, we're able to find the registry keys that we need to modify. According to pentestlab.blog, the one key in particular we need to look at is listed below. Once we recreated this in the lab environment, we were able to confirm that we are targeting this registry key, and that's the one that will gain us administrative privileges to command prompt. Taking what we know now and the registry key from the procmon output, let's go into the registry and find where this key resides. We'll be looking under the app path location. Once we get there, as seen in the screenshot below, we find that the app path/control.exe does not exist. This tells us that to modify this registry, we need to create the registry key to gain administrative privileges. Knowing that we had to create the registry key, we can use the following reged command. After committing the command, we can take a look in the registry to see if it reflects our changes made. Looking at the screenshot below, we now have a key called control.exe under the app paths location. Using procmon in a similar fashion for WS reset, we can find the registry key that needs to be modified. In this case, it falls under software classes, appx, and a long string. Looking into the registry, we see we have a default value for that key, so we're going to modify it, not create a new one. In this case, because the registry key already existed, we had to make some minor modifications. Looking at the default execute, where there once was a value, we left it blank. Also, the default entry now has the command that we want run. Congratulations, you've made it. The death by PowerPoint is over. Now we're going to get to the demo. What you're going to see in the demo is me using the tools that I talked about earlier in the presentation. I'm going to show you what it looks like using the tools, finding the values, and then going into the registry and modifying it. We're going to use PowerShell and command prompt to make these modifications and then exploit the UAC bypass. Alright, let's go. Before I start demonstrating the UAC bypass methods, there's a couple disclaimers I need to make. First, we'll be using a Windows 10 version 1809 box. This is significant because only versions 1809 and later are vulnerable to the UAC bypass methods I'm demonstrating today. That being said, I cannot confirm that Windows version 1809 is vulnerable to all UAC bypass methods, just the ones you'll see in the demonstration today. Also, we'll be using a domain admin account to make the emulation easier. The goal of this video is not to recreate the attack as you would see it in the wild, but provide you the knowledge of what a UAC bypass method is and the information that you need to detect it in your environment. I also wanted to show you that we currently have default registry values related to the executables we're going to exploit. If you remember, SDCLT relied on a control.exe registry value under the Microsoft Windows CurrentVersion app path location. If you look to the left of the screen, you'll notice that there is no control.exe registry value. We'll have to add that to exploit SDCLT. And here are the default registry values for wsreset.exe. Here we're going to have to make some modifications to gain administrative privileges in command prompt. So I know that I covered SigCheck in the slides, so I want to show you how it's used and where to find the auto-elevate property. We're going to run it against the executable that we want with the -m flag. The -m flag says that it's going to dump the manifest and give us all type of information about this executable. Looking at the output, we can see that the auto-elevate property is true by looking at the fourth line to the bottom. So we're going to run the same command using the same flag against SDCLT now. So we ran the command successfully, and we can look at the auto-elevate property again and see that it's labeled true. Now I'm going to cover using Process Monitor or procmon. But before we start actively monitoring processes, there's a configuration change we need to make so we don't get the blue screen of death. The configuration change that we need to make can be found under File and Backing Files. What the Backing Files configuration does, it is asks us where we want to store the logs produced by Process Monitor. We have two options. One, we can use virtual memory, or the second, we can store them in a directory somewhere on the machine. In this instance, I'm focusing only on the 2 executables I'm going to exploit, as well as one operation and the path to the registry keys that I'm going to create or modify. So to get Procmon started, we come over here to the magnifying glass. If there's a red X over it, it means that we're not actively monitoring processes. So let's get it started. Now that it's actively engaged, let's run the executables to see what logs we produce. After running SDCLT, we can tell it was successful because the backup and restore settings window popped up. Now let's move on to WS Reset. Once again, the executable ran successfully and opened up the Microsoft Store, which is what it's supposed to do. Looking at Process Monitor, we see that the registry keys that are reflected in the logs reflect what the research is telling us. So these are the keys that we're going to create, and these are the keys that we're going to modify to gain administrative privileges in command prompt. I'm going to start the demonstration by exploiting sdclt.exe because it's simply creating a registry key instead of modifying. I'm going to use the regadd command in PowerShell to add the registry value needed. If we look at the path, we can see at the end there's the control.exe. Looking at the /d, or the data field, we can see that I've added the value for the path to command prompt. PowerShell is telling us that our operation was successful, so let's go to see if those changes are reflected in the registry editor. So we don't see any changes reflected, but let's refresh the registry to see if it populates. So after refreshing, the registry key is there and it points to the path of command prompt. Now let's see what happens when we run the executable again. Awesome. Instead of the backup and restore settings window that we saw previously, command prompt has opened. And if you look to the top left corner, you can see that it has administrator privileges. So this was a successful UAC bypass. Now that our first UAC bypass was successful, let's do the same thing to WS Reset. When it comes to WS Reset, something I learned when recreating this UAC bypass in the lab is that you need to modify the delegate execute registry first. If you fail to do this, your UAC bypass will not be successful. After executing our command, we have been successful in modifying the registry values for delegate execute. Now we're going to modify the registry value that had the parentheses around it named default. Looking at the data field again, you can see that we've populated it with a command that will open up command prompt and hopefully at an administrative level. Our second command was successful, so let's go back to the registry to make sure it reflects the changes that were made. So currently the registry shows the default values, but once we refresh it, we should see the changes made. So there we are. Our changes are reflected in the registry, and all that's left to do is run WS Reset again. Let's see what happens this time. All right. So just like before, a command prompt window opened first so that WS Reset could do its thing, but instead of opening the Microsoft Store, we now have it opening a command prompt at administrative level. So before we move on to the detection section of this video, I want to make some changes onto the user account control settings to test whether these methods still work at different levels. So we're going to move the user account control settings up one notch at a time, and then we're going to run the executables to see what happens. So we ran both executables again, but I didn't see any changes. So let's move it up one more notch. So we move the notch up again, and we're right under Always Notify. Let's see if there's any changes. The first thing I notice is that we get a UAC prompt to change the UAC settings. Let's see if that affects when we try to run the... The first thing I notice is that we get a UAC prompt to change the UAC settings. That's a good thing. But let's see if that affects the executables when we try to run them. So once again, it seems that nothing's changed. We got administrative privileges in the command prompt. And lastly, we're going to move the notch up all the way to always notify to see what happens. Again, we get the UAC prompt to change the UAC settings, which is a good sign. Well, look at that. We got a UAC prompt when we tried to run WS reset, asking us if we would like this to make changes to our computer. By hitting no, we should mitigate this, but let's see what happens. Alright, no command prompt with administrative privileges. Let's see if that does that with SDCLT. Once again, when we try to run SDCLT, we got a UAC prompt asking us if we want to allow it to make changes. This is a good sign. We got a UAC prompt again when we try to run SDCLT. This is a good sign that even though we made changes to the registry, Windows recognizes that this is an executable that could make potentially unwanted changes to the device and is asking for authorization from an administrator. Now remember, we're a domain admin, so we can hit yes and make the changes that we want. But if I were a standard user, it would ask for admin credentials to move forward. I have one more Easter egg for you before we jump to the detection section. The regadd command that we used earlier in the demonstration will be detected by Windows Event ID 4688 or Sysmon Event ID 1 in the command line section. Now there are ways to modify the registry using PowerShell commandlets, and I'm going to show you that so we can generate the traffic and find it later. To save some time, I'm only going to run this method against one of the executables in this video, and that's going to be SDCLT. So first we're going to go through and make sure that that registry key that we created earlier is gone. Looking under app paths, I don't see the control.exe, so let's go ahead and run this command. According to the output, we were successful in adding the control.exe. Let's see if that reflects in registry. Looking at the registry, it is confirmed that we did add control.exe successfully, so now let's modify it. Using the PowerShell commandlet set item property, we're going to modify that registry key that we just created. Okay, we didn't receive any output, but we also didn't receive any errors. So let's go back to the registry and confirm our changes. There it is. And once again, just to test to make sure, either way, using any of these methods, as long as you have the right amount of privileges, you can make these changes, but if you don't have the right logging, you won't detect it. So let's modify control.exe real quick. In case you didn't catch it, what I did was I changed command.exe to calc.exe and then back to command.exe. Either way, the changes we made in the registry should produce logs. Alright, let's get to Splunk and find all this malicious behavior. Now that I've demonstrated how to execute the UAC bypass through various methods, I want to show you a couple of different ways to detect that activity on your network. First, I'm going to focus on WinLog event 4688 and Sysmon event ID 1. Both of these events are triggered when processes are created and capture command line if configured correctly. Looking at the first line of the query, I filtered out everything except EventCode 4688 or EventCode 1. Also, I have a couple registry key paths that I've wildcarded that correlate to the activity we created in the demonstration. I've also organized the output to show us both the process path and the parent process path, as well as the process command line. Looking at the process command line column, we can see all the registry keys we've created or modified, as well as the event codes that they correlate with on the far right. These event codes confirmed that we found the activity that we were looking for, specifically around the process create. Another way to detect the malicious activity that I demonstrated is through logs that contain information related to registry key modification. In this example, we'll use a WinLog event ID 4657 and Sysmon event ID 13. Both of these logs contain enough information that we can find the malicious activity that we demonstrated and find which process created it. So looking at the output, there's a couple process paths that I want to get you familiar with. Looking at the output, you can see we detected registry key modifications from various process paths. Now let's talk about the Easter egg I mentioned earlier related to the PowerShell commandlets. When we focused on EventCode 4688 or EventCode 1, we were able to find the regadd commands. Now let's talk about the Easter egg I mentioned earlier related to the PowerShell commandlets. When we looked at the EventCode 4688 or EventCode 1, we noticed we were able to detect the regadd commands. What we weren't able to find were the PowerShell commandlets that we used to modify the registry key, either new item or set item property. To detect PowerShell commandlets or scripts being run on your machine, PowerShell script block logging needs to be enabled. Once it's enabled, you can find it in EventCode 4104 under Microsoft Windows PowerShell operational log location. Using this query to focus on EventCode 4104 and the registry paths that we wildcarded earlier, and a little bit of regex magic and Splunk, we're able to separate the values as such. Looking at the output, we were able to successfully detect the UAC bypass through PowerShell script block logging. The registry path and the registry key value are all aligned with the activity that was conducted on my Windows machine. And that's it. Thank you for sitting through my Death by PowerPoint, watching my demonstration, and letting me teach you how to detect this type of malicious activity on your network. Links to the references that I used throughout this video can be found in the description below, as well as some sample queries to help you and your threat hunting team. And lastly, a huge thank you to you viewers out there to help support Cyborg Security. Every little bit counts. We like to have your views, but more importantly, your feedback. So please let us know what you think in the comments section below. Also, if you like what you saw, like us and subscribe. Once again, this is Lee Arkanal, and thank you very much, and everyone stay safe.